this part. Efficiency. Okay, efficiency is the first thing to discuss here. So efficiency, how much useful work is done with energy supplied. How much useful work is done. So, for example, right, if you want to turn on the fan, what we want from the fan is the spinning of the blade so that it produces wind. That is what we want. We want the wind. Okay, we want the wind from the fan. What we don't want is the heating of the motor. We don't want it to heat up. We don't want heat. We are hot enough, so we don't want heat. The heating of the motor is what we don't want. Okay, so you imagine the input. Try to write down here. The input is the electrical energy that go to the fan, and then the fan change the energy to mechanical energy, which causes the blade to spin and produces wind. That is what we want. So mechanical energy is something which is useful, whereas the thermal energy, the motor will become hot after you turn on the fan. So the motor become hot. It's something which is useless. We don't want this. Okay, so let's say, for example, let's say I put in number. If you have 1000 joule that's applied to the fan, 600 joule become mechanical energy, 400 joule become heat energy. Then we can find out the efficiency. Okay, so according to the efficiency formula, right, so you have to put useful energy output on top. The useful energy is 600. Okay, 600 over the energy input, which is 1000, multiply with 100, then you get 60%. So the efficiency is 60%. So the second formula, as you can see here, efficiency equal to useful power output over power input times 100%. So if the question gives us power, of course power is in the unit of watt. So if they give you power, then you can use this formula to find the efficiency. So if they give you energy, then you use the formula on top. If they give you power, then you use the formula at the bottom. They will give you the input power and then the output power. Okay, so of course here I just let you know some formula which is related to the power. So we have to know power equal to, as you can see here, power equal to work done over time. Work done over time, or sometimes you may see power equal to energy over time. So energy divided by time, then you get the power. So if you have power and power, then you can use this formula. So this one, power, you put at the bottom. This one you change to power, then you put on top. Okay, so let's see the next one. Work. Work is done whenever a force makes something move. Okay, so for example, if you push a toy car, so the toy car start to move, so work is done. So must make it move, because our formula for work done, right, involve distance move. Okay, work done equal to force times distance moved by the object which experience forces. So work done equal to force times distance is the formula. So if there is no distance move, If it's not moving, then no work is done. Okay, so for example, in what situation no work is done? If you carry the baby standing there not moving, no work is done. If you carry the baby and move around, work is done because there's a distance. Okay, distance traveled. So the unit for work is the joule, and 1 joule of work equal to, so they try to explain 1 joule of work. So when this is 1, right, then the force is 1 Newton, the distance is 1 meter. So that's why you see the words. Force of 1 Newton move an object by 1 meter, then it creates 1 joule of work. Okay, so now power. Power is the rate of work, how fast work is done. So if you do it quickly, if you work quickly, then the power is high. So the units for power is watt. 1 watt equal to 1 joule per second. Formula: power equal to work done over time taken. So it seems like we have 4 formula only, and then finish already for this part. So let's see how is the question then. Okay, so a ball player bunches a ball of mass 0.60 kg. Its center of mass moves down through a distance of 0.90 meter. So as shown in figure 1.1, ignore A resistance throughout these questions. Calculate the decrease in gravitational potential energy of the ball as it moves down through the 0.90 meter. So
we have to use the formula for gravitational potential energy.
Yeah, so which is
MGH.
MGH. So the M 0.60, the G is 10, the height 0.90. Then after that we just press calculator. Okay, then we get 5.4 joule. 5.4 joule is the answer. Okay, now B. The ball hits the ground at 7.0 meter per second. So that is the velocity. Calculate the initial energy given to the ball by the player. Okay, so initial energy given to the ball. Okay, so we have to use the kinetic energy formula, which is half mv squared. Okay, so we substitute with values. So 1 over 2, the mass 0.60, the velocity 7.0 square. Okay, then we just press calculator. 0.5 times 0.6 times 7 square. Okay, so we get 14.7. We get 14.7 joule. So I have to put the unit, 14.7 joule. So this is the energy, 14.7 joule. This energy, this kinetic energy is given to the player, given to the ball by the player. Okay, so now let's look at the next page. Part C. On another occasion, the player throws the ball into the air to a height of 4.0 meter above the ground. The ball then falls to the ground. during the impact 22% of the ball's energy is lost. Suggest one reason why energy is lost during bouncing. Okay, so when they bounce, why energy loss? So you have to suggest reason. Okay, so there are many possible answers that you can put for this case. For example, one of the easier question is, when it bounce, you hear the sound, so it changes to sound energy. So that's why certain part of the energy is lost as sound energy. Okay, so that is one of the possible answer, which is easier to take. Okay, sound. Oh,
What about heat energy, sir?
can also. Heat is another answer. So energy lost as sound. Okay, so if you want to say heat energy, so what happened is, first you have to mention about friction. Friction with floor. Friction with floor and the ball causes energy lost. Energy loss. This is energy loss as work done against friction. Energy loss as work done against friction. So if you say heat, is that okay or not? Actually, in the mark scheme that I mentioned, ignore heat or air resistance.
Okay.
So even you write it, they ignore it. They ignore. So
Okay. So is it possible energy is lost in the form of kinetic energy?
loss as kinetic energy.
Yeah.
Not possible actually. When it bounce off, kinetic energy is not counted as the energy which lost. It's counted as something which we want it. It's useful one. Loss is the one which is under the category of useless. So we want the kinetic energy so that it continue to move after it bounces off. So saying that will be not suitable actually.
Okay.
So we look at C part 2, calculate the heights to which the ball rises after the bounce. Okay, so first we need to know 22% of the energy lost already, so we still have 78%. So that is what we call the energy remain. Energy remain is 100 minus 22, 78%. Okay, 78% of the energy remain. Okay, so after that, we have to count out the amount of energy in joule. Okay, so from the previous part we have 14.7 joule. 14.7 joule. This is the energy. So we times 78%. Then we get 11.466 joule. So this is the energy that remained. And after that, we use this to find out the height, mgh. So where the m is 0.6, the g is 10, the height we need to find out. Okay, so we find out the height then. 11.466 divide 0.6 divide by 10. So we get the height. Okay, so what happened here is there is a mistake with this working. So the reason is because just now I take 14.7, right? 14.7 is from the previous one. The previous occasion is where the player throw the ball down by from 0.9 meter and throw the ball down. So I misunderstand. It's supposed to be this situation now. On another occasion, the player throws the ball into the air. So which means now it's supposed to be like this. The player throws the ball into the air to a height of 4.0 meter above the ground. The ball then falls to the ground. Fall to the ground, hit the ground, and then bounce off. And we want to find the height. So we can't use the previous values. So that is the part which made mistake. Okay, we can't use the previous value because the previous value is a different scenario where the ball come down. Our current scenario is we throw the ball up and then come down and then bounce off, and we want to see the height. Okay, so let's see how is the calculation. I put it in blue color then. So this part still okay. The first point, energy remains, is 100 minus 22, which is 78%. So because let's say during the impact 22% of ball's energy is lost. 22% lost. So imagine something like this. 22% lost. 78% remain. Okay, so that is the 78%, which is still okay to be used, but the 14.7 we cannot use anymore. 14.7 cannot use. Let us recalculate the mgh first. Okay, so the GPE is mgh 0.6, the ball with the same mass, 0.6, 10, and 4.0. Okay, so 0.6 times 10 times 4.0, it is 24 joule. 24 joule. This is the original amount of energy, 24 joule, but only 78% remain. So energy remain is 24 times the 78%. You can do 0.78 or you do 78 over 100. That's the percentage problem. 24 times 78 over 100. So 18.72 joule. So you use 18.72 joule and apply mgh again. 18.72 equal to 0.6 times 10 times height, and then you get the height, divide by 0.6 divide by 10, then we get 3.12 meter. This is the answer given. So this one is the correct answer then. Okay, 3.12. Yeah.
How did you times 24 with 78 over 100?
Because 78%. 78%. So that's why I times 78 over 100. That is 78%. You know, it's 78%, you either times 78 over 100 or you times 0.78. Two choices. Yeah, so that's why we do that. Okay, so now let's continue.
So then you equalize it with the gravitational formula.
Yeah, correct. Okay, so we look at part 3 then. An observer who sees the ball bounce says that ball should be slightly warmer after the bounce. Explain why the observer's statement is true. Okay, so
Because of friction.
oh yeah, most people will thought friction, but the mark scheme say ignore friction.
Okay.
That means if you write friction, you get nothing. They say ignore friction.
Answer the question Roman 1, I suggested friction with flow. I mean, you wrote friction with flow and the ball causes energy loss. That is okay.
Yeah, that answer is in the mark scheme. Yeah, so that's why I said you may feel like, oh, I'm a bit confused now. Here they take friction, here they cannot take friction. So that's why I suggest you to take this energy loss as sound. When it bounce, you hear the sound, boom. Okay, then that is energy loss as sound. Yeah, so which is not that confusing. Okay, now for this situation, if they ignore friction, so what can we put? They expect us to write the conversions of energy. Okay, so
Heat.
yeah,
Heat.
convert as heat lah.
Heat also is equal.
Something like this part of the energy is converted to heat in the ball. Yeah. Okay. Conversions of energy. So this is acceptable. Okay, so we have done this one. Now let's see more so that you get more idea on all this. Okay, so what else can we do? Let's see the next one. Okay, question 2. Figure 5.1 shows a model's cable car system. It is driven by an electric motor coupled to a gear system. Okay, the model cable car has a mass of 5.0 kg and is lifted from the bottom pulley to the top pulley in 40 seconds. It stops automatically at the top. Calculate the average speed of the car. Okay, so to calculate the average speed of the car, we have to use speed equal to distance over time. So we write down the formula first. speed equal to distance over time. So the distance is 6.0. The time is 40. So 6 divided by 40, and then you get 0.15 meter per second. So that's the average speed. Okay. Now part B, gravitational potential energy gained by the cable car. So gravitational potential energy, we must use the vertical distance. So cannot use the 6.0 meter anymore, must use vertical distance. Okay, so because it's GPE equal to mgh, right? Must use the height, mgh. Okay, now the m is 5, g is 10, height is 2, so you will get 100 joule. 100 joule. Okay, so now let's move on. We look at the next page. The useful output power of the driving mechanisms. So we want to find the useful output power. Okay, so in order to find out the power, so we need to know that power equal to energy over time. Okay, there's the formula. Of course, since they ask for useful output power, so we have to use the useful energy to put on top. The useful energy here is the gravitational potential energy, because the energy is used to raise the cable car. So the energy here is the GPE. Okay, so which is the previous answer, 100 joule. The time is 40 seconds. So 100 divided by 40, then you get 2.5 watt.
So how come the useful energy is the GPE?
Because the main intention of doing this is to raise the cable car to a particular height. So that is GPE. We need GPE. GPE is the useful energy output.
Okay.
Yeah. So part B, how would the electrical power input to the motor compare with your answer to A part 3? So the input should be greater. Input is greater. Imagine that there should have some energy loss. Part of the energy is lost, so the input energy should be greater than the output. Okay, so just like that, and this one settled already. Okay, so figure 2.1 shows a conveyor belt transporting a package to a raised platform. The belt is driven by a motor. State 3 types of energy other than gravitational potential energy into which the electrical energy supplied to the motor is converted. So gravitational potential energy is there because the package go to a particular height. So they don't want you to say this. They want you to say something else. Okay,
Kinetic
kinetic energy, which is correct because it's moving. So kinetic energy.
mechanical energy.
Sorry.
Mechanical energy.
Mechanical energy. Mechanical energy is same with kinetic energy. So once you say kinetic energy, you can't say mechanical energy anymore. So another
Electrical energy, sir.
electrical energy is the input. You don't say the input. Electrical energy is changed to others. So we can't say that electrical energy change back to electrical energy. So we want to change it to other energy. Okay. One of the famous answer is the heat energy. You may easily think of, okay, the conveyor belts have frictions with the pulley and have heat. So this should be one of the famous answer, heat energy. And again, you may also put some easier answer like sound energy. For sure you hear sound. If
I also put internal energy.
yes, which is accepted. Internal energy is another answer.
How internal energy is possible in this situation, sir?
Okay, so how? First, we need to know internal energy has two parts, which is the kinetic energy of particles
Gravitation.
plus potential energy of particles.
So the potential energy here, isn't it? Is it like gravitational potential energy or just potential energy?
It's not the gravitational potential. The potential energy here is the just now I mentioned it in this way. Potential energy here is the intermolecular forces of particles or the separation of particle. Okay, so that affects the potential energy. So for example, if the particles are further apart, potential energy will increase. Okay, so over here, right, internal energy increase, we can take it in this way. First, the conveyor belt will become hot. When it's hot, kinetic energy increase. Kinetic energy of the particles in the conveyor belt increase. Okay, and at the meantime, because of the particles, which is hot, move faster and faster, that separates further apart. So the potential energy of the particles should increase also. And hence the internal energy increase. Okay, so are you able to take it now? It's the energy in the particles. Okay, so should make more sense now after you look at the same thing for a few times, hopefully. Okay, so for the rest, we don't want to discuss first as we don't have enough time. So I just leave it for you to do your self-study.